All right, let's take a look at 9.1, looking at vectors. So again, in this part of the class, we're really doing kind of an introduction to a variety of topics that you may have worked with in some detail before in other classes. So you may have seen vectors in engineering or physics. What we're going to do in this class is just actually a little introduction. So if you've seen this before, it's going to be pretty simple. Even if you haven't, I think this is really an easier section. So starting out with some notation. So my first vector here is the vector u. So we use the arrow over the vector there just to indicate that this quantity represents a vector. Okay, and then the vector that I have written there with the angle braces, we call this the component form of a vector. We'll talk about one other notation you can use for writing vectors a little bit later. So here I notice that I have, an x component or a horizontal component, and then I have a y component, or I could say a vertical component. Okay, so the first thing I want to do is sketch that first vector u. Okay, so what does u say? U says go right 3 and up 1. Okay, so quite like the way I have the axis set up here. Let me see if I can that'll do. Line that up a little nicer. So I'm graphing this vector u. So I go right 1, 2, 3. And up 1. So that would be here, the terminal point. Okay, now to indicate that this is a vector, I use an arrow pointing in the direction of the vector. In other words, I went right by 3 and up by 1. So that's where I place the arrow pointing in that direction. Okay, so this is one representation of the vector u. The thing with vectors, though, is that unless it's specified, I could really start at any initial point. So notice that, what if I started over here? Well, the vector u says go right 3 and up 1. So actually, this would be the same vector u. So the key fact there is, well, a vector just tells me, let's see, maybe I should write something. What does a vector tell me? A vector tells me a length and a direction. Like, in other words, it tells me, okay, so from where I'm starting, how far do I have to travel and in what direction? But it does not limit my starting point unless the problem statement specifies an initial point, like in number 2. So we would say, all these different vectors that I'm drawing here would be considered equal. Those are all the same vector u because they have the same length and they have the same direction here. Okay. All right, let's look at number 2, the vector v. Okay, so the vector v says go left 2 and down 4, but this guy does have an initial point specified. So I need to find the initial point, -1, 3. Notice something with the notation. Notice that this is a point. So remember, points we write as xy pairs with parentheses, right? Versus when you look at the vector over here, a vector in component form, we use the angle braces and we list the x and y component. Okay, so from my initial point, negative 1, 3, what do I have to do? I have to go left 2 and down 4. So looks like I would land here. Okay, now the vector is pointing in this direction. Okay, so let's see what else I can fill in. So this is the vector v. The initial point is negative 1, 3. The terminal point where that vector ends would be what? Negative 3, negative 1. Notice I'm using parentheses for a point versus the vector itself up here is written in component form using the angle braces. So there would only be one way I could sketch that vector v because that initial point is specified. Okay, what about number 3? So number 3 says, sketch the vector with initial point negative 4, 2 and terminal point negative 5, 6. Okay, so let's see what that guy's gonna look like. Okay, initial point is negative 4. 1, 2, 3, 4, 2. Terminal point is negative 5, 6. Be here, right? So then from the initial point to the terminal point, I'd be going in that direction. And let's give this vector a name. Say call this vector W. So that one, again, there would only be one way to graph that vector because I have to go from the specified initial point to the specified terminal point. Let me go ahead and write out that vector W in component form. In other words, I have to look at the change in x and the change in y. So I go, what did I do? Looks like I went left 1 and up 4. So my vector W would be negative 1, 4. Okay. Okay, what's next? So here I have two vectors, a vector u and a vector v. And I'm asked to do some vector algebra. All right, so maybe I'll start by just sketching the vectors u and v. So, I mean, I could start those vectors anywhere, right? But the thing is, I mean, unless I had a reason to do otherwise, I think I would just start them, at the origin. So let's see, the vector u says go right 2 and up 0. So there's, one representation of the vector u. The vector v says go down 1. So the simplest representation of the vector v would be like so. Okay, so then let me see if I can do this algebra. So actually adding vectors is very easy. I can actually just add them component-wise. In other words, I add the x components, add the y components. And so my resulting vector would just be 2, negative 1. Okay, so what I did there is I added the vectors algebraically. I spelled that right. Don't think so. Oh, well. Okay, added them component-wise. So what if I plot that vector? So I go right 2 and down 1. So there's the vector u plus v. So you might notice that it kind of looks like there's some relationship graphically with the vector sum with the vectors u and v themselves. And so there actually is. So let me show you another way that I could add those vectors u and v. So I could actually add them graphically. So what about add u plus v graphically? Okay, so let me show you how I would do that. So what I would do there. Okay, I look at the vectors u and v. Now I can pick either vector to start with. It doesn't matter which one I start with. So say I start with the vector u. That's here, right 2, up and down 0. Now, from the tip of u, I'm going to attach the vector v. V says go down 1. Okay, so now it turns out that if I connect the initial point with the terminal point here, I get the vector sum, u plus v. So I can see there that vector is indeed 2, -1, which is what I got algebraically as well. So again, it doesn't matter which vector you start with. So I could show you starting with v instead. I mean, actually I could start anywhere. So I don't know, say I start over here and I take the vector v. V says go down 1. There's the vector v. Okay, from the tip of v I attach u. That says go right 2. Then I connect the initial point with the terminal point. That vector there is the vector sum. But you can see that's the same vector, right? Right 2, down 1. So that's how I would get the vector sum algebraically. What about something like number 2? This is very easy, multiplying a vector by a scalar, by a number. Well, if I want to multiply u by 2, again, I can just multiply component-wise. So it's just the vector 4, 0. But I mean, that kind of makes sense, because if I come down here and if I want to draw that vector, well, let me see. Here's the vector u again. The vector u, let's go right 2 and up 0. So wouldn't it make sense that twice that would just say, go right 4 and up 0? So there's the vector twice u. Okay, what about the vector -v? Well, that's just multiplying v by a -1. So wouldn't that just be 0, +1? And that makes sense as well, because, let's see. The vector v says go down 1. There's v. So what would the opposite of v say? The opposite of v would say go up 1. Makes sense, right? Okay, what about a little bit more algebra? Twice the vector u minus 3 times the vector v. Okay, so I'm just going to do this component-wise. So that'd be what? 4, 0 minus, distribute the 3. Okay, 4 minus 0, 0 minus -3. Looks like 4, 3. Okay. So, I mean, I could graph that, just go right 4 and up 3. But I was kind of interested in, so here I did the algebra, did this algebraically. I'm interested in, well, how would I do this one graphically? Okay, so to do this, I'd start with twice the vector u. Okay, so twice the vector u would be go right 4, right, and up 0. Okay, from the tip of that vector, I need to attach the opposite of 3v. So 3v would say go down 3. The opposite of 3v then would say go up 3. Okay, so if I'm adding the 2u and the negative 3v now, I would just connect the initial point with the terminal point. And there's that vector. Okay, so let's see, what does that vector say? It says go right 4 and up 3. So looks like I got that correct over here. Okay, here's the other notation. So we've been looking at component form. So there's another notation we use, which is writing vectors in terms of, we call these the unit component vectors. It's just another notation. It's exactly the same thing. Okay, so I, the unit vector I, is 1, 0. So this doesn't have anything to do with the imaginary number I. This is called the horizontal unit component vector. It's called a unit component vector because it has length 1. And then, as you might have guessed, the vector j is 0, 1. And so that guy's called the vertical unit component vector. Okay, so looking back up here, I mean, I can rewrite the vectors u, v, and w kind of immediately. If I want to, I can rewrite them in component form, or I can leave them in terms of I and j, and I can do the problem that way. It doesn't really matter. Notations are interchangeable. Okay, so looking up here at, say, the vector u, 5 times the vector I. So that means u could be rewritten as 5 times 1, 0. So wouldn't that be equivalent to just 5, 0? Okay, so, I mean, you can really read these off. Like, look at v. V is 0, negative 3, because it's just negative 3 times the vector j, right? So it just has a vertical component because it just has the j in there. Okay, so I mean, looking at w, I can write w immediately in component form if I want to. Okay, because this guy, wouldn't that just be 2, negative 4? I can just match up the x and y components with the coefficients on the unit vectors I and j. Okay, so I mean, if I wanted to graph these guys, here's the vector u. Here's the vector v. And then the vector w. would look like that. Write 2 and down 4. Okay. And then I can do the algebra over here. These other quantities. Okay, so u minus 2w. So I can either do this in component form, same as what we did above. Let's see what that gives me. 5 minus 4, 1, and then 0 plus 8. Did I get that right? Or I could leave these guys in terms of I and j. So let's see. U is 5 times the vector I, and W is twice I minus 4j. And so that would give me 5I minus 4I plus 8j. Combining like terms, let's see, it's going to be 1I plus 8j. Okay, so I mean, this vector, u minus 2w, I could either write it in component form or equivalently in terms of I and j. Same thing, different notation. So that would kind of just depend on if the instructions ask me for something specifically. So I don't know if I need to graph that. I mean, I just go right 1 and up 8. Let's look at 2 twice v here. Twice v. So again, I could do that component form. Or I could leave 2 times negative 3j. And so that would be negative 6j. So these two things are the same, different ways of writing the same vector. Okay, here's something new. Here I'm being asked, these absolute values are asking me to find we call these the magnitudes of the vectors. So let me clean this up. We have some space here. Okay, so as you might have guessed, the magnitude of a vector, again, that's the absolute value. So we're really measuring distance. So this guy, we call this the magnitude. So in terms of a vector, if we're measuring the distance from the initial point to the terminal point, well, that would mean when we're finding the magnitude of a vector, we're finding the length of that vector, right? So the question here is, can you find the length of the vector u? So this is an easy one, right? Because I mean, I've graphed the vector u over here already. That vector is actually horizontal. So I can actually just count the length of that. It's kind of a special case. So the magnitude of that vector, wouldn't that just be 5 versus, oh, I don't know, should I throw an extra one in here? Let's call this 4, 5, and 6. So say I want to find the magnitude of v, because that one's also very easy. So let's see, let me plot v. V is go down 3. There's the vector v. Okay, so again, I can count the length, 1, 2, 3. So the magnitude of v would just be 3, the number 3. W is slightly more interesting. So let's see, where is W? Okay, W says go right 2 and down 4. There's the terminal point, there's the vector W. Okay, so with that guy, in order to find the magnitude, really what I would have to look at is the right triangle formed here. And I would actually use the Pythagorean theorem, because what I'm looking for is the length of W, the length of this vector here. Okay, so I'm going to set up the Pythagorean theorem. Okay, so that would say the length of W squared is what? 2 squared plus negative 4 squared? It's 4 plus 16 is 20. So then the magnitude would be the square root of 20, which is root 4 root 5, 2 root 5. And that would, of course, be positive because the magnitude, again, is measuring a length. Okay, and then one more. The magnitude of my vector u minus 2w. So where was that guy? I guess that guy was up here. So I'm going to need to clean this up a little bit, I think. Have some space to graph it. Okay, that'll be good enough. So to graph that vector u minus 2w, let's see, that one says go right 1 and up 8. 1, 2, 3, 4, 5, 6, 7, 8. Be here. There's that vector. Okay. So I can put in a reference triangle here again. Right 1, up 8. And I'm looking for the magnitude. So in other words, now I'm looking for this length here. So I'm looking for the magnitude of this vector, u minus twice w. So again, I'm going to just set up the Pythagorean theorem. So I'm using my 1 and my 8. What is that, 65? So then the magnitude of u minus 2w is root 65. And again, these lengths, these are numbers, right? Finding the length. In other words, I'm finding a scalar value, just a number, right? Okay, find the magnitude and direction. Well, we've just been doing the magnitudes. More interesting part here will be the direction. I mean, okay, starting with my vector u. That's a vector again, that guy's in component form. So if I was to graph u, let's see where that would go. That would be right 4 and up 4. That'd be u. Okay, so the magnitude, I mean, just did that, right? Be 4, 4. So if I wanted to find the magnitude, I would just do the Pythagorean theorem. So that magnitude would be 4 root 2. Okay, the more interesting part is the direction. That's just asking me the angle that the vector u makes. So this is actually also very easy because can't I just set up tangent? So the angle would be pi fourths, or if you like, 45 degrees. Unless the instructions specify, I could list either radians or degrees there. Okay, what about v? Okay. So v is written in terms of I and j. Can leave it like that if I want. Doesn't matter. So I'll need to clean this up a little bit, I guess. Or maybe I'll make a new little coordinate plane here. It's not going to look as nice, but it'll be good enough. Okay, so to plot v. So v says go left 1. Look this up then, huh? V says go left 1 and down by what, 1.7-ish? That'd be here. And so there's the vector v. So again, this is equivalent to -1, negative root 3. Okay, so for finding the magnitude, it's just Pythagorean theorem. So the magnitude would be 2. What about the angle? So tangent would be negative root 3 over negative 1, so root 3. So now I have to be careful because there are 2 angles for which tangent is root 3. I mean, there are actually infinitely many, right? But these are the first 2 that come to mind. So be careful. The angle here is not pi thirds, because if it were, the vector would be pointing up, be pointing into quadrant 1. So actually, based on the graph that I've drawn there, I can see the correct angle is actually 4 pi thirds. So the direction of that vector is actually 4 pi over 3. Or if you like, what is that? 180 plus 60, 240 degrees? Either or. Find the vector with magnitude 10, direction theta equals 60 degrees. Okay, this is actually going to be pretty easy also. This is just some triangle geometry again. Look. Just a really rough sketch. Okay, my angle, 60 degrees. My magnitude is 10. So the goal is, can we figure out the x and y components? Well, isn't this just a triangle problem again? So wouldn't it be like cosine of 60 degrees is x over 10? sine of 60 degrees is y over 10. So wouldn't x just be 10 cosine 60 degrees? And y just be 10 sine 60 degrees? So actually, it's very easy. I can make a little generalization here. So if I know the magnitude and direction of a vector, I can immediately write that vector in component form just by filling in the magnitude. That's like the r. And then the cosine of the angle theta. And then again, the magnitude. And then the sine of the angle theta. Okay, so I actually have general form that I can use. Makes this super easy. So back up here, the vector u then was just what? It's going to be 10 cosine 60 degrees, 10 sine 60 degrees. And then since 60 degrees is a special angle, of course, going to go ahead and evaluate. See if I can simplify. Okay, so there's the vector u, and that vector is written in component form. Okay, so then again, it just depends on the instructions. I could write that equivalently in terms of I and j. It would look like so. Okay, so those are both ways of writing the same vector, different notations. All right, what about number 2? So again, if I'm given the magnitude and direction, it's going to be really easy to find this vector. I'll give it a name. I'll call it P. So I'm just going to use my formula here. So I'm going to have the magnitude times the cosine of the angle, the magnitude times the sine of the angle. And then I just go ahead and evaluate. So, what is that? Root 2 over 2? And negative root 2 over 2? Look like so. And so again, if I wanted to, or if I was asked to, could write that instead in terms of the vectors I and j. That just depends on the instructions.